Good afternoon, everyone. Welcome to today's session on deep learning. Today it will be a practical session taken by Ginny ma'am. Ginny ma'am, I have given you the right so that we can start with the session.
Sure.
Okay.
Yes, is my screen visible?
Yes, ma'am, it is visible.
Okay. So last time we did feed forward neural network. Today we are going to do convolution neural network. So in feed forward neural network, while feeding the images, we first translated those images into a 1D array, right? From the 2D array, it was converted into a 1D array. Now, suppose the image size is quite high, right? We use very small image size. If the image size is very high or we want high resolution images, right? In that case, we would require a very large array to store a single image, right? So it will be very difficult. And also, the sometimes some of the part of the image is important as compared to whole image. So we use this convolution neural network especially for the images, right? And feedforward neural network are mostly used for the numerical data. But we can use it for images also, as we have already seen. So today we start with the convolution neural network. So for the convolution network, I am taking a simple data set that a binary classification problem where you have to differentiate between the images of cats and dogs. Right? Simple data set we are taking. And for the CNN, if we want a local data set, like for example, in the feed forward neural network, the MNIST data set that we work on, the CPA data set that I told you to work on, right? If you have done that, so those data were available in the KRAS library, right? So if we want to use some of the data set that are directly available under KRAS data set, you can directly load that data. But suppose if you want your own data, right? For example, if you want to do some classification problem or any other problem that requires your own data, in that case, what you have to do, you have to create like you have to store the data set in the form of a folders, right? For example, if we suppose want a data set to be a training data set and a testing data set. So what I will do is I'll create two folders, one, and you can name anything that. For example, I have named here training set and test set. You can name anything that you want. Inside that, we will provide two classes or n number of classes that you want to classify. And in that, you have to specify your images, right? And you can have, like, for example, there are three types of data. Like, for example, you can have training data, testing data, or you can have training data, testing data, as well as some validation data to check your results on some unseen data set, right? So I have divided the data here. So I have taken in data in the almost ratio of I think 80 to 20, 80 is to 20 ratio. But I have taken 3 or 4 images for the validation set so that I can show you how we can predict on the unseen data set also, right? So to see how you will store the data, so either you can store the data in your current directory in which your file is saved, like this is my current directory. I have saved the data here. So you can directly use this data with the name. And if you are storing it at any other place, then you have to provide the complete URL link to that, right? For example, if you are suppose saving it under some other directory, like D directory or C directory, so you can copy the address of that location and you can directly use that address to get your data set. You don't always need it in your current directory. But we have kept it in the current directory, so it is easy to access the data, right? So that's why I've stored the data here. So I'm going to show you how we are supposed to save this data if we want to use some local data on our own instead of just using the MNIST data set, right? So what I will do is, if suppose I want to divide the data into training and test, I have created two folders, one for training and one for testing. So if I open this, you can see inside this there are two another folders, that is one for each class. Like for example, if you have 10 classes with you, you will have 10 folders here, and each folder will contain the images of that particular class, right? So for example, now I have two classes here, one cats and one dogs. So I have created two folders inside it, one for the cats category and one for the dogs category. You can name here whatever category you are taking. So if I open this, so here you are only able to see the one image. So let me show you this in the folder itself. So you can see the complete data set. So here is a folder. So I'm showing you here training set. There are two folders that we were talking about, one cats and one dogs. So I am opening this one. So you can see now that, are you able to see my screen? The folder which I am sharing, or you are just seeing the Google Chrome?
Visible, ma'am, visible.
So you can see all the images of cats here, right? So there are around 3,999 images. So you can see that there are different types here. So you can see all these images. Uh, I don't think you are able to see this screen. I think you are able to only see the Google Chrome. Wait. So I think now you are able to see the screen that I'm showing you. So here you can see we have a training set, and inside that we have two folders. So one is for cats and one is for dogs. Inside that we have multiple images here, right? So similarly in the dog section also we have various images of the dogs, right? And for the test set also, similarly, I have created two folders for the test set also. So here you can see some of the images for the test set, right? So in this way, you can add n number of images in here, right? Okay. So I have shown you the images, right? How we are going to, how we are storing the images. I'm going back. Yes. Now I am here back to my current directory, right? So you can see, so from this current directory, I want to access the data set. For that, there is a class in the Keras library that allows you to directly call the images from the directory. For that, first of all, I am using the class from Keras dot preprocessing dot image import image data generator. So what does this image do? First of all, let me run it. Yes. So this is as you have seen here that it is under the keras dot pre-processing, right? Dot image. It means we are talking about pre-processing of the images. So this image data generation library is a special library that is used to generate the data at the real time, right? So how it is generating the data? It will do the image augmentation for us at the time of training the model, right? So what it will do is it will randomly take any image and will do the data augmentation techniques on it. So different types of data augmentation techniques are available. So let me show you what type of values are present inside this image data generator library. So I have opened this the documentation of the keras. So you can see here that this library comes under the tf.keras. You can directly write keras also as I have written by because keras run on the top of the TensorFlow. So you can either call tf.keras or you can directly call the keras, no problem, right? So if you are writing it tf.keras, then you have to import TensorFlow first. Okay. So it comes under keras.preprocessing.image.image data generator. This is the library we are using. So what type of image augmentation technique is it can do for us? So let me, these first 4, 5 are not important. I'll tell you the most frequently used ones. So to see the detailed documentation, you can scroll down, you can see the every argument that is used here. I'll tell you the most used arguments. So here is this first one, zoom underscore range. What zoom underscore range does it? It zoom out or zoom in our data randomly, right? For example, if suppose there is an image that may contain some other components apart from cats and dogs also. So if you zoom out of it, you can always able to see the other components also. So it can also zoom out or zoom in. Next, the important thing that is mostly uses is horizontal flip. So what it does, it horizontally flips your data. Like for example, if you have an input, it will rotate it by 180 degree, horizontally flip it. And similarly, there is vertical flip, right? You can flip your data vertically also. Then there is rescaling of the data. Like for example, we have an image in feed forward neural network. We divided it by 255, right? So that was rescaling. So you can use this rescaling of the data, and there are other arguments also which you can use. You can try out these different arguments and you can check what this all arguments generate for you, right? So this data generator, image data generator class gives you the range of the data, image augmented data at the real time. At the real time means while you are training your data. So it is very important class that you can use for the image augmentation. Image augmentation can also be used so as to make your model more robust. Why more robust? Because, for example, you have a new image. It is of a cat, but it is rotated at 180 degrees. If you have not trained your model on any of the rotated image, then it will not be able to predict that correctly, right? It may be or it may not be able to predict that correctly. But if you have trained your data on the vertical flips also, on the horizontal flips also, then if you have a new image which is even upside down, then also it will be able to detect it, right? That is why we use the data augmentation. So I'll show you two techniques of data augmentation. You can try rest out your way. So I'm using image gen variable. Image gen means image generator. So I am taking this library, image data generator. So inside this, I am going to use two of the augmentation technique. You can try any one. The most important one we always do is like rescaling of the data. So I'm going to rescale the data. I'm going to divide it by 255, like we did in the feed forward neural network, right? And one more thing I'm going to use is horizontal flip. I'm going to horizontal flip is equal to true. By default, all the values are false. And if you want to set any of the value, you can give it the value true. If some other parameter is required, you can check that, right? I have written horizontal flip is equal to true. Similarly, you can use vertical flip is equal to true. You can use shear and zoom, or you can do anything like that, right? So I will run this. So I have my image generator object. What it will do is, while giving me an image, it will randomly flip the image, right, sometimes, and rescale the image, right? So this was the first important step in the CNN that we were going to use, that it will augment the data for us in the real time. Now I want my actual data. So for that, we are using the library flow from directory. So I'll show you that library also. So you have here flow from the directory method. So what this does, it takes the path to a directory that is where our data is stored, and it will generate the batches of the augmented data. Why augmented data? Because we have used the image data generation library that will augment the data. Now we are taking the flow from directory library, which will link us to the directory where the actual data set is present, and it will take some small batches out of it and give us the augmented data out, right? So how batches means, we are using batch gradient descent here. So it means we are going to define our batch size. You can define any number of batch sizes. So what it will do is, suppose you have defined a batch size of 32, then it will create the batches of 32 and give to us the augmented data in the real time, right? So you can see different functions here also. Like for example, we are going to define the directory, that is where our actual data is available. We are going to define the target size. Target size means, for example, now we are taking the local data set, right? So all the images may have different sizes. It is not always the case that all the images have same sizes. So what we are doing here is, by picking up the image, whatever the image size is, it will rescale it to that one. So you have to give the low target size here, whatever your overall image lowest value is, right? So you have to give the target size here. You can take the color mode here. So color mode tells you, like for example, you want your image to be colored, right? Then you can use the RGB mode. You can take your image to be grayscale, that is, it will variate from black and white range, right? And there are other default values also. You can have n number of channels here. Next is the class mode, which is also very important. So first of all, there is classes is equal to none. What it does, you have to define your class names here. If you are not defining your class names, so it will directly pick that from the directory where you have stored the data. For example, you have seen that under the training set folder, there were two folders ahead, right? One for dogs and one for cats. So what it will do is, it will take that name itself and give them as a name of the classes if you are not providing that manually, right? So that is why we have given the correct names there, so that it can directly pick up from that and we don't have to provide the class name manually. For example, if there were so many classes like 20, 30, 40, so it will be difficult to provide the classes here as a list. So instead of that, what you can do is, you can give meaningful names to the folders inside the training and testing set. So it will pick the names itself, right? Next, the next important thing is this class mode is equal to categorical. So what it does, tells you that what type of classification you want. For example, if I want a binary classification, so I will use class mode as binary. If I have multiple classes, then I will use class mode as categorical, right? Next is the batch size. You know what batch size is, that it will divide our complete data set into the different batches. Next, you can see here is that shuffle. Shuffle is like, for example, when picking up the image, either pick it up line by line, or you want to shuffle first and then pick up randomly, right? So you can use shuffle here also. Seed is for, like, for example, if you are shuffling the data, Then you want to maintain a seed also, that if suppose anybody else run it, if you use the same seed value, you will get the same images, right? Next is save to the dir. So it is like I have told you that it will do us the data augmentation at the real time. So if I want to save the augmented files also, augmented images also, so I can use save to dir. Here we can provide the directory where we want to save our augmented image to, right? And these are not so much important. So these were the arguments that were more important. You can see all this in the Kera's documentation, right? So this is the flow from directory library that we are going to use to get our data, right? So first of all, I am going to get my training data. So training data is equal to, now I want the data to be augmented at real time, right? So I am going to use a image gen, right? Through image gen, I am going to call, so image gen dot. Now I am going to use a library name flow from directory. So if you have any doubt in between, you can ask, right? Because it has all the terms as new in the starting, right? So here, first of all, for first argument was the directory, that we have to provide the directory. So I told you I have my data set in the current directory. So I'm just giving the name of the folder that I have used, right? Training set. You can see I have used a training set now here in the same directory. So I'm going to use this training set, comma. Next was our target size. So I'm going to use target size. So I'm using 64 by 64. If you want to reduce the size of the image, you can also reduce it, or you can also increase it. So I have my target image size. Next important thing was batch size. So I'm only taking the important arguments that are required. Suppose I'm taking a batch size of 32. And the last thing is a class mode. That is at which class mode is there. We have a binary classification problem. So we have a class mode as binary, right? So you can see here we have used a directory. We have used a target size. We have not used a color mode. By default, the color mode is RGB, that it will take the colored images. If you want black and white, you can give here. Next, we are not giving classes anything. Why? Because we have given the meaningful names at the background. So it will directly take the name from there. Next is the class mode. We have a binary class mode, so we are using this, and a batch size of 32. Rest we are not doing it. If you want, you can try out that. You can try out shuffle also. You can try out seed also, and save to directory also. These three you can try out on your own, right? These three. So you can learn this from the Kera's documentation. So this is how we are calling our training set. So I think it's good to go. Let's try and run this. So you can see here we have it has found 7996 total images belonging to how many classes? 2 classes. Now you can see it has automatically maintained 2 classes for it, right? So how it has maintained 2 classes? I will tell you the link in the end. It is available online, right? If you write down dogs and cat dataset, you will find it there, right? No problem. It is easy to find the dataset. Or if you are not able to find, I will provide you the link at the end also, right? So you can see here that we have it itself has created 2 classes. So how it is able to identify that we have 2 classes? First of all, we have provided a class mode here binary, and secondly, we have provided the 2 folders there that belong to different categories, right? Similarly, we are going to use for the testing data set also. So I'm going to just copy this. So I'm doing this for testing data. Right? I have named the testing data as test underscore set, right? So I'm going to provide here name test underscore set. Target size will remain the same, batch size will remain the same, class mode will remain the same. Only the name of the folder will change, right? So if I run this, so you can see now we have found 2000 images belonging to two categories, right? So we have our training data as well as the testing data. Now we have done the data augmentation part, we have imported our data. Now it's time to build the model, right? So from that, first of all, we are going to use the libraries, like I told you, from keras.models. So you can see it is also sequential model, right? Because there are sequence of layers, the convolution layer, max pooling layer, convolution layer, max pooling layer, and number of layers can be that, right? Then dense layer is there. So these all are the sequence of values. So the model here that we are going to use is still the sequential model. So from keras.model import sequential some spelling still models from keras.models. Yes, we are now able to import the sequential model. Now we are going to import the layers. I'll tell you one by one which layers we are going to use. Let's suppose start with the keras dot layers import. So you know we have the convolution layer here, right? First layer is the convolution layer. So let's first import that layer. Con to D. So this is the name of the layer that we are going to import. That is convolution 2D layer, two-dimensional layer, right? So I have imported the convolution layer. So we can add the layers side by side while we will be adding it. So first of all, what we will do is we'll provide our we'll initialize our model. So let's initialize it using a sequential, that our model needs to be a sequential model. So we have created our model to be sequential. Now we are going to add the layers to it. Just like we did in the feed-forward neural network, here the layers will be different. So we are going to use the same function model dot add. So first of all, we are going to add a convolutional layer, right? So you know the convolutional layer we are using here is conv 2D, right? So inside that we are supposed to give various arguments. So I tell you one by one. So in the convolutional layer, you know that what we are doing here in the convolutional layer, we are applying filters to the input data, right? So we are giving the input, that is an image, and then we are going to provide a filter to it. We are going to provide an activation function to it, and repeated application of these filters will give us a feature map, and we'll use that feature map to work ahead, right? So it means the first thing that is important is the filters. So the first argument we have is the filters. That is how many filters we want. Suppose I am giving here 16 filters. You can use any number of filters. You can use 16, 32, 64 or 10, 12. You can use any number of filters. So I am using here 16 number of filters. You can check these and try these values, whichever gives the best result to you, right? So the next thing that is important is the kernel size. So we are having a kernel size is equal to, you can have any kernel size. We don't keep it very small and we don't keep it very big. So what kernel size gives us is that it specifies the width and height of a 2D convolution window. That is, we are applying the convolution on the input data. So for that, it is giving us the size of the window that we are going to use here. So it will give us width as well as the height. So why it is giving width and height? Because if we see the input is like a pixels, right? There are two-dimensional pixels there. One gives you the height, one gives you the width, and there is another one which gives you the depth. Depth is like how many channels are there. For example, if you have 3 channels, the depth would be 3, right? So similarly, the output is 1 by 1 pixel, right? If we apply the first filter to the first convolution window. So that convolution window size that we are going to use here is given by the kernel size, right? So we have used the kernel size here. Then we have to provide the input shape. That is what now I just told you, input is a window, right? It consists of 3 things. One is the height, one is the width, and one is the depth. That is how many channels we are going to use. So we are providing that shape to it. So we above we show that we are taking the image to be here in the target size. You can see we are taking the image 64 by 64. So the first 2 things would remain same, 64 by 64. And one more thing, we are using the RGB channels, right? But if we are not mentioning any channel here, it means we are using the RGB channel. So it means the depth would be 3. So this is our input size, right? Sorry, input shape. And last thing what we are going to use is activation. We are going to provide the activation here. So activation is equal to value, right? So you got all the inputs. One is a filter, the number of filters you want to apply. The next is the kernel size, which you are going to use. That is the size of the window, 2D convolution window. Third is the input shape. First two gives the height and width, and third one gives the depth. That is how many channels you are using. By default, we are using RGB images. So RGB images have 3 channels. And the last one is the activation we are providing. So we are providing there the rectified linear unit. So if I run this, should go. Yes. So we have added our first convolution there. Now we are going to add the next layer. So after convolution layer, which is the next layer we use the max pooling layer, right? So the next is the max pooling layer. So I'm going to add here. So it is inside the layers only. So we can have multiple layers added in a single line using the comma, right? So I have added the con 2D layer. I'm going to add the max pooling layer, right? So if I run this, yes, we have added a max pooling layer. So for that also we are going to add it here using model dot add function. Right? Inside that we are going to use our max pooling layer. So it is M capital, P capital. We have our max pooling layer. So inside this, we are supposed to give the arguments like we did with the convolution layer. So inside this, there is only one argument we are going to use, that is a pool size. The same way we use the kernel size, we are using the pool size here. That is the max pooling, the pooling size that we are going to use on the window. So it will be pool size is equal to, I'm going to use 2 by 2. You can try out different values. So it has only one argument inside it. This. So I have added one convolution layer, one max pooling layer, right? So similarly, we can have any number of layers. Like for example, I can add max convolution layer, then max pooling layer, then convolution, then max pooling, or we can have another arrangement of max pooling layers or convolution layer as per your need, right? So you can have any number of values, right? So let's suppose we add one another convolution layer. So I'm going to copy this. Inside this, let's change the filter size to 32. I'm increasing the number of filter size. You can change the filter size as per your need. Rest all will remain same, right? The activation will remain same, the input size will remain same, and the funnel size will also remain the same. I'm only changing the number of filters here. And this, I have added another configuration layer, right? So now we have two configuration layer and one max pooling layer. Let's add another max pooling layer. Just I am copy pasting it and running it here. So you can see I have added another layer. You can add now a number of configuration layers or the max pooling layers you want, right? Let's add another set of layers and increase the filter to further 64. The number of filters to 64. Can increase or decrease as per your requirement, right? So we have added another set of layers. So run this and run this. So now I have our model, which is a sequential model. In that sequential model, I have added one convolution layer, one max pooling layer, another set of convolution and max pooling layer. It means we have gone 3 layers deep in the convolution layer. You can have any number of layers like this. So I have 3 max pooling layer, 3 convolution layers added to it. Now what we are going to use is, after we have done that, after using the max pooling layer, what type of output we are getting? We are getting a window, right? So we are getting a window, but before getting the output, I need a 1D set of arrays, array like value, right? Because from that single, if we have a single set of neurons in the layer, then only we can get a single prediction out of it, right? To do that, we are going to add the flatten layer. That is one more layer we are going to add. Flatten. So this flatten layer, what does it? It will convert that window into a 1D array. Just like we did in the feed-forward neural network. In feed-forward neural network, what we did was we converted the complete image into a 1D array and then do the processing on it. But here we are decreasing the image size to the useful pixels only. Now we have the window that contains the useful pixels, that contains some more information, and then we are going to flatten it, right? So now it will require less number of neurons as compared to if we had the original image size. So if we had the original image size directly feed into the feed-forward neural network, we would have an image size of 64 cross 64 cross 3. So we will have a 1D array that is of the size 64 by 64 by 3, right? So instead of having an array of 64 by 64 by 3, here we will have a much smaller array, right? So I am going to add a flatten layer. So model.add. So what I am going to do is I am going to add a flatten layer. So we are not supposed to give any argument. Whatever the window size is left with the previous max pooling layer, it will convert it into a flatten layer, right? So I have added my flatten layer. So now what is left? I have now flat layer, which consists of all the values in the form of single layer that have the neurons. Now I want the predictions out of it. So before compiling, we have to add the output layer, right? We have still not added the output layer from which we want our results to be, right? So I am going to add the dense layer to it. The output layer is a dense layer, right? So I am going to add a dense layer, right? So model dot add. So I'm going to add the output layer. So output layer is of the type dense. So inside the output layer what type of arguments are there? It is same. So we have the number of neurons in the output layer. So we have two classes. One neuron is sufficient to give us the answer, right? So we are going to use one neuron in the output layer. what other thing we are supposed to do? We are supposed to add the activation. So I'm going to add an activation here. Activation is equal to. Now I told you in the feed, while doing the feed forward neural network, we have the, first of all, we have the classification problem. Secondly, we have a binary classification problem. So what type of activation function will be required? Sigmoid. No, softmax will not be used here. Why? Because softmax is used when you have more than two categories, right? Then it will give you the categories, right? Different categories, probabilities in the form of different categories. So if you have two, we want the probabilities. Our answer to be in the range of 0 to 1. So we are using here activation as the sigmoid. So I'm going to add my last layer. So I have completed my model that consists of 3 convolution layers, 3 max pooling layers. Then I have added 1 pattern layer so that all the outputs can be consolidated in a single array, 1D type of 1D array. And then I am adding the output layer to it. Now we are left with this compiling the model. So we are using model dot compile. So inside compile, we have the same arguments that we have the previous time. So what type of arguments it will be? We will have an optimizer, right? So what I'm using as optimizer, Adam, we used last time, will be same. Next we have a loss, right? So which type of loss we did by using two classification problem? Binary cross entropy. So binary underscore cross entropy, right? And the last thing is the matrix. We are using the matrix. Which matrix I want? Accuracy, right? You can add any other matrix also. So I'm providing a list here. You can add any type of matrix to this list, right? So this is the final compilation. So we are done with the compiling our model. We use the optimizer as Adam, loss as binary cross entropy. So if you have more than 2 classes, you have to use a categorical cross entropy, right? So now we are to fit this model. We have compiled the model. Now we are fitting the model. So to store the intermediate results, I am using a variable, right? So model dot fit function we are going to do. That fit function, now see that arguments here are somewhat different from what we did in the feed-forward neural network. We provided there the training data, right? So we are giving here the training data also. So in that we provided the X labels as well as the Y labels, right? So instead of using that, here we are just giving the training data. Why just giving the training data? Because the X is images, which it will directly pull out from the library, pull out from the directory, and the Y is the I classes, that is cats or dog, which it is also directly pulling out of the library that we have seen by running this here. This, so you can see it is also pulling out the labels also, right? So we are just giving the training data here instead of X and Y. Now we are giving the number of epochs, that is how many time I want to train our model. Let's use 20. You can use bigger number also. But remember, it will take some time to train because it is images. So it will take different time on different systems, right? And now what we are going to use here is another argument, that is steps per epoch. So what it does it, how many, like for example, you can use all of the images per epoch, or you are using batches also. So inside one batch, how many images you want to use for training? You can use all the images also. You can use some of the images also. So that steps per epoch tells you that I'm taking 30 here, that I'm taking 30 steps per epoch by training. You can add any other thing. Now, in this convolution layer, it gives us another flexibility that in each epoch, it will train your model and it can also test your model side by side, right? So if I want our model to test side by side, for example, this training, right, and giving some results, then it will test based on those results. Then it will learn from them and come back background using back propagation, right? And then again train, then again test. So it can use the testing for you simultaneously. So for that, we are using validation data is equal to our testing data that we give, right? Similarly, just like the steps per epoch, we can also give the validation steps. That is how many steps you want during the testing. Validation underscore step is equal to, you can give any, I have given 10, right? So it is validation steps. These are the arguments that we are going to give in a fit function. What is that? One is the training data that we are providing. It contains the X as well as Y. Number of epochs we want. So first let's run it because it will take some time to run. Right? So you can see while running in the first epoch, it has taken 30 steps. Right? You can see here. So it is running. Let's run this and side by side, let's see what the arguments are again. We are fitting the model using the training data where the number of epochs we have taken is 20, steps per epoch as 30. Similarly, we are using the validation data also side by side, which is our testing data, and the number of steps are 10. So if you see here while running, there are 4 arguments. Last time in the feed-forward neural network, there were only 2, right? So here we have 4 arguments. That is the loss while training, the accuracy while training, the loss while testing, and the accuracy while testing, right? So you can see initially the accuracy was 46 training accuracy and the validation accuracy was 54. It means it was underfitting, right? And then we came down, the accuracy increased to 54. Here the accuracy is 58. So it's still underfitting, but quite near to each other, right? So we cannot exactly say underfitting. Now you can see here 58, here 60. The difference is decreasing. Similarly, it is increasing to 63 and 64. Now it has learned properly. Now it is neither underfitting nor overfitting, right? So in this way, you can see different accuracies, validation loss and validation accuracies. We have run our 20 epochs and it may take different amount of time than it took on my system because my system, the code that I'm running is working on the GPU. That is why it took less time. So it may take more time on your system. So you can start with small number of epochs and then check like how much time it is taking on your system to run, right? So I have fitted our model and we have got our results. So any doubt till here, then we can check out some intermediate results also.
एक्सक्यूज मी मैम
Yes.
मैम जब हमने मैक्स पोलिंग लेयर लगाई है वो सिर्फ प्रीवियस कन्वोल्यूशन लेयर के लिए होती है या सारी पीछे की कन्वोल्यूशन लेयर के लिए होती है?
The previous convolution layer.
ओके थैंक यू.
Any other doubt? Anything that is not clear here because we have added very new information today. Okay, if you are not having any doubts, we are going to move forward. So we have fitted our model. Let's plot some different plots out of the intermediate results, so we can see how our model is training. The filter sizes I have taken randomly. You can try any number of filter size. You can even take 16, 16, 16 or 32, 32, 32. You can have any number of filter size. Just try on different sizes and check out the results, what you are getting, right? And it is based on trial and test, right? No particular value. So let's calculate the, first of all, the accuracy. So how we are going to do for from the intermediate results dot history. So last time I tell you the value that we are going to put here is based on the name that is given here. So that way, in that case, it was not making much sense because we didn't have many values. Here you can see the values are different, right? Here the word is accuracy and we have also have validation accuracy. That is why I told you the name to be given exactly the same as this, right? So if I am going to write here accuracy, run this. So I have my all the accuracies. Now if I suppose want validation accuracy, so I'm going to do is validation. So let's add it here so you can see properly. Validation accuracy is equal to results dot history. So now we are going to give the name val underscore accuracy, right? The name that is given here. So if I run this, get our validation accuracy. So you are seeing the accuracies that we get while testing the data, right? So let's plot these accuracy. So if I want to plot, so what do I require? First of all, I have to import the library. Import matplotlib from matplotlib dot pyplot as vlt. So plt dot plot accuracy. So I have got the accuracy that is increasing, like sometimes it is increasing, decreasing, but till here you can see that around 20 epochs it is still increasing. So it means it has not converged yet. You need to increase the number of epochs so that we can see where it is converging, right? Because it is still increasing till 20 epochs. So you can add more number of epochs to see where it is converging. Convolution layer may require more than 20 epochs to learn properly, right? But it will take more time, so that's why we are running here on 20 epochs, right? And suppose in the same plot, we are also plotting the validation accuracy to show the comparison, right? What may we have given validation accuracy. So you can see here, the validation accuracy is also learning in the similar fashion like our training accuracy, right? And it has also not converged till epoch 20, right? So you need to train it more. It means our CNN has not trained very well till now, right? So you can add the X labels also, Y labels also, depending upon what you want. Like for example, you can also give, like we have two values, so you can color code these values. You can tell that the blue indicates the accuracy, training accuracy, and the orange indicates the validation accuracy, right? So you can add the X labels and Y labels to it. Similarly, we can plot the loss also. Let's see how the loss looks like. Loss is equal to results dot history. So let's see the name, the other name that it has got. The one is loss, the other is validation mark. Right? So it is. We are going to name it validation loss. Here also we'll change the name. So we have done this. Let plot please also plt dot plot loss. Let's see how it looks like. So now you can see the way the accuracy was not increasing in a very smooth way. Similarly, loss is also not decreasing in a smooth way. It's still not converged. We are still need to run this on more number of epochs, right? So we can try on more epochs at the end also after I have completed all, right? And let's plot the validation also. I have plotted both the loss, right? So it means the model has not trained well, but we have built a model, right? Now the next thing we are going to do is, before running it on more number of epochs, let's try to predict some of the values from the validation set, different set that we have created. Like for example here, you can see I have the validation set here. If I open this, you can see inside this also I have created two classes in the similar fashion I did for that. And suppose I open this, it means you can see I have added two images here, right? So these images are unseen and we have not added in either in the training set or in the testing set, right? So this one is the first image and so this one is the second image, right? Similarly, go back. We can have here also. This is our first image and here also I've taken two images. It's the second image. You can have any, so what you can do here is you can download some images from the net and you can create your validation set on yourself and then you can run the testing portion and you can see how well your model has learned, right? So I have added a validation set here. So let's add this data. So validation data. So it is my wish if I want to like rotate image augment the data here or not. So if I am using the image augmentation, so I'm using ImageN. If you are not, then you can just not use this, right? So flow from directory. So we are going to provide here the set that we have used, val underscore set. We have given the directory name. Now we are going to give the target size. So we are giving 64 by 64, right? And we can use the class mode here. We don't require batches here because our answer is like we only have 4 images. We just want to see how it is working. So I'm not defining any batches here, right? So in the test set, we don't require much of the batches. So here I'm using the class mode as binary. Yes. So you can see that we have found 4 images that belongs to two classes. I told you 2 images were there of cat and 2 were there of dog, right? So we found the 4 images. So I'm going to use the evaluate function here. You can use predict also, but in that case, then you will require the true values also. So you have to get out the true values, the predicted values, and then you can use the predict function also. So there is another function model.evaluate, which just takes the this data and give us the result, right? So model.evaluate model.evaluate will just provide our data here. validation data. So if I run this, you can see it has learned 75. It has learned with 75% accuracy. So what does 75% accuracy here means? That it is able, out of the 4 images, it is predicting 3 images correctly and 1 image as wrong image, right? Either it can be cat one or a dog one, but it has been learning with a 75% accuracy on the unseen data set. That is not bad, right? So it is giving a good accuracy with only 20 epochs. We can improve this accuracy by increasing the number of epochs also, right? So any doubt to anyone?
मैम टेस्टिंग डाटा मिक्स क्यों नहीं है? हमने टेस्टिंग डाटा को भी क्यों मतलब 2 कैटेगरीज में डिवाइड करके उसमें दिया है?
So that it could know the true labels also, right? If we are not going to give the true labels, then you can give in the form of single also, single class. So we want to see the accuracy, right? If we want to see the accuracy, we need to give the true values also. So that's why
Okay.
we have created 2 folders.
Okay.
So if you don't want the true correct answers and just want to check, you can use the predict function also. In that case, you no need to provide the true values.
मैम एक बार वो दिखा सकते हैं कैसे करना है प्रिडिक्ट वाला?
So I have not created that data in that way. But it will require like lot of information more because if we want, suppose we want to just do it this way also. Let's see if this works. Let's take one image. For that, we need to first convert image to a correct size, right? I don't think this will work. Let me check. And we also don't need to provide the 2 labels. No, it will not work like that. You have to give the single image to it and then you have to predict, right? So for that, you require the separate data. Any other doubt? I can show you the predict one also. Let me download the data, one image, and then I'll show you how we can do it, right? So in the meanwhile, you can ask any other doubt you have. And let's also run this let's run that at the end. First of all, let me show you the predict one. So you can ask any doubts you have here. And the meanwhile, let me show you the predict one also. Let me download one image and tell you how it will work. Meanwhile, please ask the questions if you have.
So is there anyone having any doubt in today's session? Senior ma'am, do we need to complete any task other than this for today?
Yes, just wait for 5 more minutes. I'm going to show them one more thing, right? One student had a doubt. I am running that. I'll show the students that also, right? So just wait for 5 more minutes. Let me write the code and I'll show you. Yes, yes, please. I'm doing the prediction here also. The one student that asked how we can predict the value without giving the true one. So see how we can do it. So first of all, what we have to do is we have to import the NumPy library, right? NumPy library. The Keras pre-processing library, from there, we have to use this image library so we can get the image from keras.preprocessing import image. So I am first of all going to load the image, right? Which image I want. So I am taking one image. So from the validation set, inside that we have cats folder. Inside that there was a name this, right? cat.1.jpg. So I am using this one image out of it, and I'm defining the target size as 64 by 64. That is the size that we have taken here. So it will convert it into 64 by 64. So before running it, we have to convert this image into an array, not 1D array, but a 2D array. So that we are using this function image underscore 2 dot array, 2 underscore array. So we are converting this image into an array. So this np dot expand is just to convert it into a shape that we require. So you don't need to worry about this line first, right? And then we can use the function model dot predict. Inside that we are going to use this test image that we have, right? So if I run this, and we have stored a result in the result section, and now I run this. So it has given us a value 0. So how we can know whether it is giving me the correct or not? So we can calculate, we can check the original class indexes that our model has given. So for that we can we can use training data also, we can use testing data also. We can use class underscore indices function. This function tells us that which class is given which label. So you can see here the cats is given a 0 label and dogs is given a label 1, and our answer is 0, and we know that we have given an actual cat image. So it means our model is predicting it correctly, right? Is that answer your doubt?
Yes, ma'am.
Okay. So any other doubt, any other student? So one more thing, you can ask your doubts. Meanwhile, let's run this on more number of epochs so that we can see whether the results are further improving or not, right? So it is running. Now you can ask your doubts if you have any. So meanwhile it's running, I'm stopped sharing. I'll share again when it's done. So there are some doubts in the chat box. Let me see that first. How to get the data set. So let me share the link with you. No, it is not necessary that you run your model on the GPU. You can run on the CPU also, just that it will take some more time, right? Like for example, it was taking 4 seconds to run one epoch, it will take like around 7 or 8 seconds, right? So you can run on the CPU also. No, it is not a necessity. It is just that I have to use other work. I have to use my system for other works also. That is why I have GPU with me. So I have shared you the link to the data set also that you require. There is one more question. It is used for copy, move, forgery detection. I didn't get your question. What you want to ask? Can you ask again, Smriti? Is Smriti here? If you want to ask your doubt, please ask again. It is not clear in the chat box what you want to ask. Am I audible?
Yes, ma'am, you are audible.
Okay, okay. The one student had doubt. If you want to ask, you can, right? Any other doubts? So let me share my screen with you again to show you the model after 30 epochs. So you can see here that we run till 20 epochs and the accuracy was around 70%. So while we have reached till 30 epochs, you can see the accuracy, validation accuracy, and the accuracy has reached till 80%, right? So it means the model is learning. So if I plot now again, you can see that we have reached more accuracy, but there is more variation now. So it means the model has still not learned properly, right? So it needs more number of epochs or it needs more number of layers to go, right? So in this way, you can try and test on different number of epochs. So you can ask any doubt you have. Otherwise, we are done for today's session. In the research field of copy, move, forgery detection in the digital images, can we use it now? So it depends what type of problem you have in your hand, right? For example, if you have some kind of classification problem, like for example, if you want to like classify whether the data is original or not, then I think the both images need to be, there need to be some form of pattern that could show that, right? For the forgery detection, right? It depends what type of images you have and what type of classification problem you want. So what we can do here is, if we want to apply CNN to it, we can divide like image into small subset, right? And then we can match the both the images, and then we can see whether both the images are matching or not, right? So in that way, we can use CNN. Rest it depends upon the application, right? But definitely we can use CNN, but we have to see how we can use it, right? So how we are supposed to give the input. The method of giving input will change, but we can definitely use CNN there also. Any other doubt? Sakshi ma'am, I think we are done. The participants have no more doubts. So if you want, we can end the meeting.
Okay, ma'am. Then can we end the session?
Yes,
Okay. Thank you so much, ma'am.
thank you.
Thank you, everyone. And you can see the attendance link in the chat window. So kindly complete your attendance within next 10 minutes. Otherwise, we'll end the form over there. Thank you.